And ultimately, if you have information, thank you so much. If you have information concerning, how a rate will go and depend on other materials, that lets you burrow down into the mechanisms. And that's, of course, all the organic chemists all go crazy over. If you have mechanisms, you can optimize a particular channel. So if you're wanting to synthesize a new drug, let's say Jez-amphetamine, all right, so you put your products within there or your reactants within the system, and you often get multiple channels. You get this type product, B, C, and you want to optimize for a particular type of a product. Well, if you know the mechanism that is going on there, then you can do that. You tune things and get things that you want working in the right direction. Well, kinetics is a big part of that. So anyway, first we're going to take it back to a lot of stuff that you did in Gen Chem. So as I always say, pull out the Gen Chem book. If you don't have one, walk one. I got a couple extra. You can so anyway, so when you have a reaction, so if I wrote a reaction, let's say, a little more interesting. So I go in there and I say, all right, what I'd like to know is make a measurement, how fast is this reaction going? Because ultimately I'm going to find out how the rate is dependent on pressures and concentrations and time and things like that. So I'll have to go to Angela and say, hey, would you mind doing me a favor? Would you go into the lab and measure this? And she goes in and measures how fast nitrogen goes away. Then she comes and reports to me that, well, it's going away at 10 moles per second. She's making up a number. Then I go to Sierra and say, would you go do that for me as well? And she says, I really want to, but fine, I'll do it anyway. So she goes into the laboratory and she decides instead to measure the disappearance of hydrogen. Well, when she measures disappearance of hydrogen, it's going away at 3 times the rate that the nitrogen is going away. So she comes and says, Angela, she's full of, didn't know what the hell she's talking about. It's actually going away at the reaction is 30 moles per second. Well, now I'm getting 2 different answers. And so I got to find, if you've got 2 clocks and they say different times, you go consult the 3rd clock. So, Juliet, my 3rd clock. And you go in and say, yeah, I'll do it, I'll straighten this mess out. You go in, and you tell me how much the rate of ammonia is appearing. And you say, well, the reaction is going at 20 moles per second. Well, you can see the problem. It's almost kind of like the 3 blind men and the elephant. You ever heard that? You never heard that before? 3 blind men come across an elephant, and one, they come over, get the elephant's tail, and he presumes that the elephant, they're trying to figure out what the elephant looks like. And the elephant is just, it's a very thin thing, it's kind of fuzzy. The other one comes across the trunk. He says, no, it's a big old thick thing, and he's shoving me around all over the place. And another one comes across a foot. So each of them have a different perception of what's going on because they measured something different. It's kind of the same deal here, sort of. We'll say it. All right, so we've got this case. So we need to come up with some consistent way of defining what a reaction rate will be. So here's what we will do. Let's say for the nitrogen, the rate of this reaction overall will be 1/1 times the negative change in the nitrogen over time. Of course, amount per time is what matters. The 1 comes from that right there. There's a stoichiometric 1 in front of that nitrogen. Well, we'll say that is also equal to minus 1/3 times the rate of change of hydrogen with Gesundheit time, if there's such a thing as Gesundheit time. All right? And now you see if I take the 30 divided by 3, I get the same 10. That works. And you can see we can do it the other side, except we'll make that positive 1/2 times the change in the amount of ammonia per time. So that gives us a constant rate definition. So I go on to measure rates, I'll need to take that into consideration. So overall, we're going to say, all right, the rate is going to be, if it's a negative, it's a reaction because it's going away. I have these as little d's. That means instantaneous. If you have a rate of a reaction, if you're measuring the amount of a material, and it's going away and it changes its concentration over time, so that might be something like this. This could be like nitrogen over time. Well, if you measure a point here and here, and you measure that, and get the slope of that, that would be a rate, but that is an average rate. To get an instantaneous rate, you don't do it, this is called a tangent line. To get an instantaneous rate, then you draw a secant line, one that just touches that curve. And what you're effectively doing, over here, you have like a T2 and a T1, and that produces a delta T as you go from T1 to T2. If I bring these two T's closer together, that tangent line comes closer to the curve, and eventually when they meet, you get what we call as the instantaneous rate. And that is denoted in calculus. And again, I've got some calculus in here, but you're clearly not responsible for it. But I'm just saying that if you see a little d, that is the infinitesimally small version of delta. Okay? It tells you that gives you more of an instantaneous phenomenon. Okay? All right. We say that concentrations play a role, and pressures as well, as far as what a rate will be. And so what we ultimately do is, for a reaction system, we write down what is called a rate law. Again, this should be coming back to you like molasses from general chemistry. So we say, well, rate law, for say that reaction, I would write as a rate constant, and in this case, I'd be multiplying by the pressure of N2 times the pressure of H2. Now, these are two powers, but we don't know what they are. So I'm going to call this power M and power N. They are not related to the stoichiometric coefficients anymore. They're related in a complex fashion because there's a mechanism going in. There's only one time I will be able to take a 1 and put it here, and take a 3 and put it here. And that's only under the case where I know that reaction is exactly happening as written. There's no mechanism. One of these bumps into 3 of those simultaneously and produces 2 of those. If it happens in a single step, then I can put the 1 here and the 3 here. We're not going to be able to do that. But when we look at mechanisms, we will be able to do that. Okay, so this then is called the rate constant. And you have seen a glimpse into what that is made up of. When we were talking about the chemical dynamics, we were talking about how many collisions were happening, particles between walls. At the end of that note, we didn't do it, but I showed it to you. We actually built a rate constant from parameters, how big the molecules were, how often they collide into each other, and so forth and so on. Activation energies, all of that stuff in that chemical dynamics chapter is contained within that rate constant. But we'll just leave it as the K from now on. Well, the objective then in any system, once I want to study a system, I would like to know what the M and N values are. This says if whatever M is, then the rate will be dependent on that power. So if I were to take nitrogen, if M were 1, if I double nitrogen, the rate doubles. If M is 2, if I double nitrogen, the rate quadruples. 2 squared is 4. So I need to know what that dependency is. And then finally, when I get that, I want to know what that rate constant is. If it's a very, very large number, the reaction goes very fast. If it's a very small number, it goes very slow. So the first objective is going to want to do that. Now, like I say, mechanisms and reactions can be very complex. So here's an apparently simple reaction of hydrogen and bromine producing hydrogen bromide. What could be simpler than that? They bump into each other and exchange reactions. Well, the reality is it's a very complex mechanism. The bromine is dissociated usually by light. Then the bromine radicals, hydrogen produces HBr, it produces a hydrogen radical, and they just kind of go in this chain sequence. And if you actually look at the rate law for that, it is really quite complex. So we've got a square root of a rate constant for the first step, okay, and then here's hydrogen pressure, and there's bromine pressure to the 3/2 power, and I got this denominator. So things can get really ugly really quickly. But we'll be able to produce that in a fairly easy fashion using some approximation methods as we get to the second part of this. All right, so our approach then will be we're going to see how do elementary step reactions occur. That means the ones that occur in single steps or behave that way. We'll be able to draw some general conclusions. Those actually will be the conclusions of the equation that we gave you back in general chemistry while you're still wet behind the ears. So we'll revisit those. But then we'll want to go into the laboratory, once we've kind of bootstrapped this thing a little bit. We're going to go into the laboratory and examine experimental methods to determine what the rate law is. We want to know this. We want to know what M, N, and K are for that particular rate law. So we're going to need some laboratory methods to do that. That's where we're going to be doing a lot of the plotting. We'll be pulling up Excel. I'll do a couple of them today for you, just to get you started on it. And then once we have the lab done and said, okay, this reaction behaves in this way, then I'm going to want to start proposing mechanisms and testing those mechanisms to see if they confirm what I observe. If they do, it gives me good evidence with what's going on down there. So that's what we're going to be doing. So we're going to begin then with these elementary steps, which are called concerted reactions. And the reactions kind of occur in this way. And I will generalize this. And I will probably produce something that you have seen in general chemistry. The reaction that goes like this is for a reaction of, A going to products, and I'll have to say N amounts of A going to products. So a very simple reaction system in this case. Now, if I have for this reaction, I would write a rate law equal to K times A to the nth power. Now, if this N is 0, we call it a 0 order. These powers are called orders. So if N is 0, we call it a 0 order. If N is 1, we call it a first order. If N is 2, second order, and so forth and so on. Okay? So when we go through this, now this has then to be solved through a calculus means. Casey here does for you. So I separate variables and do an integration on that, or then I just do this. I have my hand-waving operator. I said, then calculus happens. And out we come to shoot. When we come out of the chute, we have one of two possibilities. I go, if N is equal to 1, if it's a first order reaction, we get kind of a unique result. We get what is called an integrated rate law that says that the log of the pressure or concentration or absorbance, something that is related to the amount of material, the natural log of that is the natural log of the initial amount. How much did I start with? And then minus a K times T. So now that's different from this. And let me compare this. This came from R is equal to K times A to the 1 power. That's what I mean first order. Now, this one here is different from this. It's obtained from this because this has time explicitly in it. This has concentrations at a rate constant and all that, and how fast it goes. But this says, you give me a time, I will tell you how much A is there. That's what we need. So this is called an integrated rate law. Now, if N is not equal to 1, there's some other value, then you get a little more expanded expression. It says that 1 over A to the N minus 1 is equal to 1 over A0 to the N minus 1. Then it becomes plus N minus 1 K times T. Okay, I have this on the other side, that's all right, it doesn't matter. Now, let's do this for one, see if we can reproduce, see if there's anything that you recognize here. So for this system, let's say, well, what if, let's have a 0 order. Let's say N is 0. Well, if I had N equals 0, this is 0 minus 1. That's A to the negative 1. So that means that would be A in the denominator of a denominator. It would look like this, 1 over A. That's where N is 0, that's A to the negative 1. So that bubbles up to the top, so that becomes A. And on the right-hand side, that does the same thing there. That becomes A0, the initial amount. Then I have 0 minus 1, so I get minus K times T. So that's the 0 order rate law. You may recognize that from general chemistry. Let's do one more that was usually given in general chemistry for, let's say, the second order reaction. Well, if the second order, it says A to the 2 minus 1. 2 minus 1 is 1. So I get 1 over A. And on the right-hand side, I get the same thing on the other side. So I get 1 over A0. And now it becomes plus 2 minus 1, or plus 1, or plus KT. says that for a zero order, second order, these are then the integrated rate laws. And so if I had K, I've gone into my lab and I've gotten it. If I had the K here, then I could tell you what time it is, and I could tell you how much material I will have at present. And different mechanisms will produce those different results. By far, overwhelmingly, the first order is more common. We're going to play with that in radioactive decays and polymerizations and things like that. We'll see a few of these things going forward. So there's kind of the general scheme that we would use those. And then down, like I say, down through these nodes, you're going to see calculus from time to time, but focus on these highlighted areas. Those are the ones you want to zero in on when you're starting to look at the equations or in calculations and things you're going to be doing. Now there is a second type of a second order reaction that is called second order of an alternate type, and this is where I have not A plus A going to products as I had here. If there's a second order for this, it would be A plus A going to products. That yields this right here, the second order. But if it's A plus B, and now I'm reacting two different things, which you would imagine would be quite common. If I react two different things together, then I get a slightly different rate law. It takes a little bit more mathematics to get there, and we end up again with the highlighted expression of which you want to pay attention. It says down here, the rate law looks like this. It says that this is for, again, I'll come back to that. This is for A plus B going to products. And we have the log of the ratio of B over A. The log of the ratio of the initial B over the initial A. These are all ratios to each other. And then finally, plus the difference between the two, B0 minus A0 times KT. All right, so for a single component, these first and second order reactions take place. For if I have A plus B going to products, it looks like this. Now, just to kind of demonstrate how this works, if you look at all of these, the way I have written all of them have been in linear form. All of them are of the form y equal b plus m times x, straight line. So if you write it in linear form, you can associate the y's with the x's and the m's and the b's. So for example, this right here, if I write again my y equal b plus mx straight line, to get a straight line, of course, you plot y versus x. Well, if I compare these in zeroth order, if I plot the concentration or pressure or absorbance or whatever versus time, I should get an intercept that's A0, and I should get a slope that's the negative of the rate constant. Just reading that out directly. If I use a second order reaction, this tells me if I plot 1 over the concentration versus time, I always associate that time with that x in these, then I should get an intercept of 1 over the initial concentration, and I should get a slope that is the rate constant itself. And finally, here, which is what I'm going to show you right now, if I plot the log of the ratios of the two reactants versus time, I should get this as an intercept, and this should be the slope in there. So here's an example of that. So in doing so, I've got a reaction. This is between ethyl ethanoate and sodium hydroxide. And the concentrations of the ester, that I call the ethyl ethanoate, is 0.15 molarity, and the sodium hydroxide, and for the other reaction, is 0.055 molarity. And here I have them here. So here's time going 0 seconds all the way to 140 seconds. So if I were to have gone into the laboratory and measured these concentrations, which I can do spectrophotometrically or by pH, or if it's a hydroxide, or whatever, then I plot these things down. So what I then do is I take this number divided by that number, that's B over A, and I get this 2.727. Then I do it again for each one. Each one, I get a ratio. Well, this says my y, which I'm going to be plotting on my y-axis, should be the natural log of that. So I come over here, I said, all right, I take that number, 2.727, take the natural log of it, I get 1.003. And I continue down the list. Down here at 9.559, I take the natural log of that, that's 2.257, and so forth. So what I will then do, according to reading this, is I will plot this on the y-axis and time on the x-axis. And so when I do that, I get this plot that you see here. You see it is indeed a straight line. Now, if I calculate the slope of that line, this slope of this line calculated out is 0.010452 reciprocal seconds. Well, that's this number. So if I found that number to be 1042 seconds to the -1, and that's equal to B0 minus A0 times K. That's what that's telling me. So to find K, I just take that number, 0.010452 seconds to the -1, divide that by B0 minus A0. That's the initial concentrations, which I have up above as like the 0.15 and 0.055. Well, I do that, and I get a value of K of 0.11, and there's units of reciprocal molarity, seconds, which it should be. Okay? So that's an example of how you use the graphics in order to produce the data out of that. Okay? Now we'll do a couple of these, and there's a couple of methods we'll look at, but I want to introduce one more thing before we look at some laboratory methods. That's a concept of a half-life and a relaxation time, or an X-life. I'll talk about that. If you were to follow a reaction over time, you say, okay, let's say I'm monitoring a radioactive decay product. I got uranium-235, I'm going to bury it in the ground, and I'm going to let it stay there until it's safe. So I want to ask the question then, what happens to it? Well, if you were to monitor the amount of material, concentration or amount or grams or whatever over time, then it acts as I'd drawn out earlier. It starts off at some initial amount, A0, and it begins to decay. Well, as it decays, the reaction rate slows down. Now remember, when things are reacting, the reaction rate is dependent very heavily on how many things are colliding together. If you have a lot of collisions, the reaction goes more quickly. If the collisions slow down, they did. So if I had a room full of people here who moved all the desks over to the edge, I say, everybody run around the room. You're going to be bumping into each other like crazy. There'll be some reaction, somebody get ticked off and punch somebody. There's going to be a reaction, right? But if I clear half of the room and say, run around again, right, then you'll have less collisions. And finally, if I have one person running around all by themselves, they bump into a wall, that's about it. Right? But so as the amount of material goes away, the number of collisions go, then by the way, it goes with temperature as well. If I have you walk around the room at a colder temperature, you have less collisions than if I have you run around the room. Same thing applies. So as the reaction proceeds, it goes away. Well, it goes away in an exponential fashion in most instances, but if you follow this out, it just slows and slows and slows and slows and slows and slows. And if I ask the question, how long will it take for the reaction to go to completion? The answer is almost forever. Because you have 6 million billion of these things, a mole of material, or often much more than that. And so as it slows down, the collisions become less frequent, particularly if it's a solid material. And so it just doesn't slow down. So it sounds like a kind of a dumb question to ask. How long will it take for all of it to go away? A much more reasonable question to ask is how long will half of it go away? So what we do is we say, okay, here's A0, I'll go to the halfway point. So this is A0 over 2. And I will move this over to the line, I'll draw a line down, and we call that T1 half, or simply the half-life. Now for a radioactive decay and for nuclear reactions, it's a very unique relationship. But for the elements, it's a little bit more general. So let's develop a half-life expression. And you'll find something very interesting for that first order. So let's begin with this one. So this is first order. I have to do two, one for first order and one for any other order. So for first order, I will do this. I will say at T1 half, A concentration is whatever I started with divided by 2. Agreed? By that definition. Well, I'm going to put that in here. So for that, I get the natural log. Now the concentration is A initial divided by 2. All right, now on the right-hand side, I get the log of the additional amount of material, A0. And then it becomes minus K times T 1/2 now. Now it becomes a T 1/2. Okay? All right, now I will solve for this. And so I'll subtract this from both sides. I can get rid of this now. So this now will become the natural log of A0 over 2 minus the natural log of A0. I just simply subtracted that from both sides. Well, I had a subtraction of 2 logarithms. And of course, if you have a log of B minus the log of A, that's equal to the log of B divided by A, by the rules of logarithms. So this becomes the natural log of A0 over 2 divided by A0. And in a very unique circumstance that's possessed only by the first order reactions, the A's go away. And this becomes then the natural log of 1/2. Now, so then we have the natural log of 1/2 is equal to minus KT 1/2, because I still have this part here. All I did was subtract this over, so that is now true. Well, the log of 1/2, another rule of logarithms, is if I take the argument of the log and flip it on its head, the log changes sign. So this is equal to the negative of the natural log of 2. All right? Just doing the rule of logs. I used 2 rules of logarithms. Well, I did that because I have 2 negative signs here. Now the negative signs go away. And I see immediately, solving for that the half-life is the natural log of 2 divided by k. Now this is a unique and actually quite handy expression, because this says that I don't care how much stuff I began with. It doesn't matter. At a certain designated time, log of 2 over k, half of it's going to go away. And let's say if we call that the half-life. Let's say I had a material, the half-life was 10 years. So if I had 100 grams of material, 10 years later it's 50 grams. 10 years after that it's 25 grams. 10 years after that is 12.5 grams. You follow? So every 10 years it goes down by half. Very convenient. On the other side of this, if I measured a half-life, I could invert this and I can find out what the rate constant is. So doing my half-life measurements, I can determine rate constants for this particular systems. Now I will tell you this, that I chose, because it's most commonly talked about, a half-life. But I could have used a third life. How long will it take for 1/3 of the material to go away? Or a fourth life, or an X life, or E life. So if I, in general, T1 over X will be the natural log of X over K for first order. That's kind of the general scheme. So no matter what I put in there. So if X is half-life, so that's 1/2, then it becomes 2. Third life would be log of 3 over K, and so forth. One that is of particular interest is where if X equals 3, if X equal the natural number E, 2.71 irrational number. If that's the case, then T1 over E is given a unique symbol called a tau, it's called relaxation time. And this is kind of interesting because this turns into the natural log of E over K. Well, remember, the log and the E are opposites of each other, just like the base 10 log and the 10 are opposites of each other. The log of the E ends up just being 1. So you get 1 over K. So the nuclear people like this one because they just measure what are called relaxation times. It's handy for certain kind of experimental processes as well, where you'll take a system and you'll zap it with a laser, for example, and you'll have relaxation time coming back, and you can measure kinetics and things like that. So the first order is very, we'll come back to this, and we'll use this when we're looking at some radioactive decay. Now I want to do the same thing over here. It'll be a little bit more complicated, but I want to do the same thing for a general order reaction, because we will be able to use that later to determine information about a reaction system. It'll be another kind of lab technique. So let's do the same thing for an N order. So for N order, we still have the same thing. It's at T1/2 A is A0 over 2. Nothing's changed there. All right, so I'm going to do it now to this, because that's my general reaction rate law formula. All right, so in the first case, I'll have 1 over, this will be A0 divided by 2 to the n minus 1, okay, minus 1 over A0, that's equal to n minus 1 k, now t 1/2, okay? So this one gets this is the n minus 1 here. Okay, well, I can write this here. I can take that 2, pop it up to the top, and write this as 2 to the n minus 1 minus 1 over A0 to the n minus 1. In other words, I bubbled the 2 up into here. I had a common denominator of A0, and then I just subtract it in there. And that's equal to the n minus 1 k t 1/2, and now I have what I need, and I'll be able to use later. So if I use this a little later, I will find that the half-life is 2 to the n minus 1 minus 1 divided by A0 to the n minus 1 times k times n minus 1. So put that off to the side. Then if I say I have a fourth order reaction as an initial concentration of 0.1 molarity and a rate constant of blah, 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 then you can just put a 4 in here and you can get a half-life out of that very quickly. And of course, as usual, I just showed you where it came from, but I have it derived, and here's your final, there's the usual point, go to the highlighted equations, okay? So there's that, and then the reaction time, that event. Okay, now in this time, we got a little bit of something that we could use. It's time to go into the laboratory. The first two methods that are often introduced in general chemistry, I'll present to you right off. One you'll recognize immediately. But one is called a trial plotting method, which I'll illustrate for you in just a moment. And one is called the method of initial rates in this particular instance. So we'll take a look at this one. Now, the trial plotting method is based on all those linear equations of which I had. And we'll keep it limited to 3, but for n of 0, 1, and 2, we have these. And that log of A is the log of A naught minus KT, and finally 1 over A is 1 over A0 plus KT. So those are the 3 that we want to look at. Now, the trial plotting method is not all that cracked up to be good type of thing, and I will explain to show you why that's the case with KT. But here's the idea. I will go into the laboratory, I will start making measurements. I'll measure concentrations, and I will keep track of the time as I do that. I will then create 3 plots that correspond to these. For this, I will create a plot of concentration versus time. For this one, I'll create a plot of the log of the concentration versus time. And for this one, I will create a plot of 1 over the concentration versus time, in keeping with that it being in the form of a straight line. There's all your y's, my t's will always be my x's. Now the theory is this: if I take a set of data and I plot it, one of those will be straight. The other ones will have a curve to them. The one that is the straightest line will be yours. So if this one comes out to be the straight line, they'll say, aha, it's first order. And furthermore, I'll be able to get the rate constant directly. Okay? So I'm going to pull up some data, and we'll do one of these, and then I'll show you the problem with it. So I'm going to grab a little. That's where I pulled up my fancy Excel worksheet. And I'll begin. So I've got a set of data. Let's see which one I want to use here. All right, here we go. This is a reaction it's a mercury chloride reaction, but I just give the following data. These are in seconds, so 0, 1, 2, 3. So I got 0 seconds, 1 second, 2, and 3 seconds. At those particular times, I get the following pressures: 15.1, 11.8, 9.21, and 7.2. All right, so that's raw data, raw lab data. Now what I want to do is I want to create 3 columns. One I already have, the actual pressures. Now here I'll make it the log of the pressures, and here I'll make 1 over the pressure, and then I'll make 3 plots. So I hope I don't mess this up. I'm going to Excel a lot. So over here, I will say this will be equal to the natural log of B1. See, so it's going to go to B1, take the log, and that'll be the result there. All right, if I now just copy and paste that down, my mouse trained here. So I'll do a copy and paste that down. So there's now the logs of all those. Okay? Now over here, I'm going to say this is equal to 1 divided by cell B1. So it goes over B1 and takes the inverse of it and produces that number. So then I will copy that again and paste it down, and I'm ready to go. Now we'll start making some plots. All right? So I'll come over here a little bit. We'll do a insert. One of these. Kind of big. Let's calm this puppy down a little bit. All right, put them over here. Now I want to select my data. So I do a chart data range. I kind of always mess this up a little bit. So I'm going to take my times and concentrations. See if that does that right. No, I didn't. Hang on. Do it a different way. Select data. Always find that first one's a hard one. The series name will give us a series values. I will have as these. I think that's right. And okay, and then the X categories. I will make times. There we go. All right, so there is my chart. What I'm going to do here. Then once I'm done with them, I'll be able to just do a copy paste. So I'll say I'm going to add a trend line. So in other words, curve fit it. I'm going to make it linear, and I'm going to say, please display the equation on the chart and the R squared. Remember, that's a correlation coefficient. So I do that, and I get a value. There it is. Close this up now. And I say, well, put this up here. So I get a correlation of 0.9881. Not too bad, fairly strict. But let's do this again. And now when I've got this, I can just do a copy paste on this. So I do a copy and a paste, and I'll then change my data. So I'll select my data, and now over here, I'll edit this. Instead of using that B1 to B4, I'll make that the log ones. I'll do that. Okay, and there it is. Now look at the correlation coefficient. 1. Okay, all right, I've still got this in my memory, so I'll do a copy and paste on that. And let me edit the data here. Select the data, let me edit this, and now I'll pick that data. And it named it, I don't know why I edit the series.
You missed it.
Oh, that's why. That was a hell of a title. All right, and now I get the R is 0.9882. All right, so 1.9881, 0.9882, this is the most linear. But you see the problem with this? How tight those could be? Because if you were looking at this visually, it'd be a little bit difficult to tell. This is not too bad. You see a little bit of curvature there. That looks pretty straight, and that is straight. But without doing that regression, it becomes difficult. Well, that's the problem with this method. The problem with the method is you have to have extremely good data over a long period of time. And oftentimes you get, even if you have errors in your data, because the instruments give you some, natural fluctuations and errors and stuff like that, that could be a problem. So it's an okay method, but it will get you within there. And by the way, this is concerning now, this is problems number 2 and 3. I want to make a mention over this. So in problems 2 and 3, you're going to do trial plotting methods. But in problem number 2, you have this reaction of 2A going to B. Okay? And what I've got for you in the data, let me just go ahead and put this out. I have time of 0, 10, 20, and 30, and 40 minutes. So that's your time. And then I have over in the column below B values. Okay? And the B values are 0, 0.086, I'll just draw a couple of them, 0.142, and on. Okay? Now, the problem with this is in order to do the trial plotting method, we need the concentrations of A. Okay? So you need to extract from this the concentrations of A. Well, the amount of A that I started with, I tell you, is 0.5 molar. And you're going to lose 2x amount of that. And you're going to produce then X amount of B. Right from that? Standard ice diagram type of approach. Okay, by still following the stoichiometry. Well, if X is B, like say 0.086, well then the concentration of A is 0.5 minus 2 times that number. You see? So you'll create a third column or row of A, where you start, this would be 0.5 to begin with, this would be 0.5 minus 2 times 0.086, and on. That gets you to the A's, then you can do this. All right? And so just be aware of that. And on that type of problem. So in other words, you have to manipulate the data sometimes in order to get the things that you need in order for this thing to work. A similar problem arises in problem number 3. In problem number 3, I've got a specific reaction. There's a decomposition reaction that I give you a Journal of American Chemical Society reference on that of C2H4O. This decomposes to methane and carbon monoxide. Okay? So in this, though, however, I have given you the total pressure, the pressure of everything. All right? So I've given you P total. So what we need is the pressure of that material there. All right? So we start off at time t equals 0. That has nothing but ethylene oxide in it. So it started off, I will call that P0, where P0 is 115.30 torr. Okay? So 115.30 torr is what I begin with in there. Now, as the reaction proceeds, we're going to lose X amount of this. X amount of this is produced, and X amount of that is produced. Same scheme, same idea. So the total pressure in there, which is what is given in the table, pressure total is the P0 minus X plus X plus X. Well, for many of you have been doing that in equilibrium. So those go away, so that's equal to the initial pressure plus X. Well, that tells you there, therefore, X is the total pressure minus the initial pressure. That makes sense? Then finally, the pressure of the ethylene oxide, EO, this is EIO here. The pressure of that is going to be P0 minus X, or P0 minus P total minus P0, where I've substituted this in for X. Do a little bit of algebra. This P0 minus and then minus negative becomes 2P0 minus P total. So that's how you have to manipulate the data a little bit. So what you'll do is you'll take that initial pressure of 115.30, double it, and then subtract from that the pressure total. Now see if this makes sense. If I take, let's say at time t equals 0, well time t equals 0, that's the pressure. So the total pressure is that. So time t equals 0 is 2 times that number minus 1 times that number, I get that number back. So once you have that data conditioned, then you go back to this and then just substitute that data in there, your plots will pop up and you can assess, by the correlation whether it's going to be 0 first or second order. Okay? That's a trial plotting. It's going a little bit out of favor, kind of thankfully in Gen Chem, but it's still being used. That's worthwhile doing. The next one you're familiar with, we'll talk about next time, and that's one where you're doing the methods of initial rates. You're taking something, you're measuring a rate, you're changing one thing to see how the rate changes, and you put that all together. I'll show you a generalized way of doing that so that you don't choke on your own calculator when you do problem number 4. All right. So we will continue that then Monday. We get to have our party on Friday.